Ladies and gentlemen, fans and aficionados of Precalculus, we're going to do a review of our last semester final. And this is going to be a review in a little bit different aspect. We're not going to go over all the 28 problems. We've taken the 7 top scoring students, and we're going to have 10 problems here that are problems that were missed by at least 2 of these top 7 students. So we're going to go over starting with problem number 3, which of the quadratic functions in the answer choice has a real zero with a multiplicity of 2. And so we have the answer choices A, B, C, and D. And if you know the graphs at all, pretty much, you should be able to eliminate answer choice C, because you're going to have you're not even going to touch the x-axis. So you're looking for what I've done is I've graphed. I have on the calculator. I've pre-entered those 4 functions, and I have them right here. We press graph, and we see all 4 of them. And here in the black one is choice C, which I eliminated already. And then we have let's see, answer choices. This red one here, the upside down one, that's answer choice B, and that is incorrect because we don't even have one real zero. So B is eliminated also. And so now we're between answer choice A, which is in blue, and answer choice C, which is in lavender here. Well, the blue one here, what you have is, this is the one, the answer A, that most people chose, because we have 2 real zeros, but it's 2 real zeros, each with a multiplicity of 1, whereas the one here at the left, the lavender one, is a single zero with a multiplicity of 2, which just touches but does not cross the x-axis. Therefore, your correct answer choice for this one is D. D does not touches but does not cross. So anyway, as far as being able to do this without a calculator, if we take this function to the D, we can rewrite this in factored form as quantity x plus 5, x plus 5, which we can rewrite as quantity x plus 5 squared. And then with that squared of the single zero at -5, that's how we have a multiplicity of 2. So that's one that actually quite a few people missed. Let's go on to the next one that was pretty highly missed. I'm going through a lot of ones here that were not super easy ones that a lot of people got right. So congratulations to the class for that one. But here we are to 9. Which of the following rational functions contains a removable discontinuity? And I'm just happen to be looking at the test of Brandon here, and what Brandon did is he synthetically divided all of these and saw which one of these synthetic divisions gave a remainder of 0, and then he knew that would be that if you have a remainder of 0, that would constitute that divisor being a factor of the numerator, therefore a removable discontinuity. So just I'm not going to do all of the ones that I saw Brandon do. I'm just going to do answer choices B and C. So here we have, we're dividing this x squared plus 2x minus 8 by x plus 3. So we're going to take our 0 from the denominator of -3, and here in the synthetic division bracket put in 1, 2, and -8. And then we're going to go through the synthetic division process, and we get 1 here. -3 times 1 is -3. 2 plus -3 is -1. -3 times -1 is 3. And so we get a remainder of -5. Since our remainder is not 0, we do not have a removable discontinuity. So therefore B is not the correct answer. And we go to answer choice C. It's very similar to what we did here for check out answer choice B. We're going to put 2 here outside the synthetic division bracket and put 1, 2, negative 8. And then we go ahead and bring down as before. 1, 2 times 1 is 2, 2 plus 2 is 4, 2 times 4 is 8, negative 8 plus 8 is 0. So this one, since we have 0 as a remainder, that means we have a removable discontinuity, and so C is the correct answer. Now, when you can graph these also and see what happens. And I'm going to just graph in the calculator. I think I have one of these pre-entered here. Let me get rid of this. Clear, 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 clear. And down here we have this. Let me see here. Which was 9. Yeah, I'll just enter, show what it looks like here. We'll come up here to the. So if you enter answer choice, oops, where's that? Here we go. So I'm enter answer choice B again. We have, well, I'll enter answer choice A and just see it variety. So if we put answer choice A here, which is x squared plus 2x minus 8, and we divide that by x minus 4, and we graph this, what we see is and we can't see quite far enough to the right. Let me go ahead and just change the window a little bit to get a little better view here. I'll put 15 here and 15 here. I think we should be able to see that break. I'm still not quite seeing it up here. Let's try 25 just to be. See both pieces here. There we go. And so what you have is you have a removable non-removable discontinuity at x equals, in this case, 4. So that's not a removable discontinuity where you see a vertical asymptote like that. Now if we go ahead and change that to the correct answer choice, which Brandon determined by synthetic division was C, you graph this, and you just see a line that goes straight through here. Well, it doesn't look like any kind of discontinuity, but if you go ahead and look at the table view, you can see where x equals 2. When you see a discontinuity in the table view, but you don't see it graphically, that's evidence of a removable discontinuity. So that's number 9. Next one we're going to look at is 13. Let's go to 13 here. Which coordinate grid represents the graph of a parent exponential function? And this is one of the 13, actually I think we get 15 parent functions of precalculus. This was, now C is a parent function, but it is a square root function. That is not it. And D is the parent logarithmic function, but A is the parent exponential function. And what that could look like is if we go over here and put in, we'll put e to the power of x, which is the natural exponential function. So it looks like this. If we go back to standard window, zoom 6, there it is. So answer choice A as our correct answer for 13. That should have been a pretty easy one, but yeah, a lot of people miss it. 14. A function is shown And here we have it. Which statement best describes the discontinuities of the graph of f of x? So this is going to be similar to the one we looked at on problem 9. And we can analyze this pretty well without a calculator. And I'm gonna do this without a calculator first, and then show you. So, which statement best describes the discontinuities of the graph of function f of x? Well, if we can make the denominator equal to 0, which we can, and we can see here that x cannot equal -5, because if x is -5, we're going to be divided by 0, and so A is not a correct answer. And so if we go ahead and factor the numerator, we're going to have this factored in the numerator to x plus 5 times quantity x minus 2. And then we carry over what we had in the denominator, which is x plus 5. And so this x plus 5 or x plus 5 are going to cancel each other. So this discontinuity at x equals, or x cannot equal -5 rather, that is a removable discontinuity. So that's what it is. There's no jump discontinuity. It is not an infinite discontinuity. An infinite discontinuity would be a vertical asymptote. So let's go ahead and graph that just to verify graphically what we've already determined here. I'm going to go ahead and clear this out and go activate this green one right here and see what that looks like. Again, we have a discontinuity where x equals -5. What kind of discontinuity is this? We graph it. We don't see any break here at x equals -5. But if we go to take the table view, we're going to see at x equals -5 we have an error. It's a division by 0 error. And so that's a graphical verification. Next we're going to go to problem 17. What is the domain of the function h of x equals x squared over x squared plus 3x? Here I have the fortune of kind of looking at Brandon's analysis. So he looked at this denominator, and if he says x squared plus 3x cannot equal 0, then if we factor out an x here, that's going to be x times quantity x plus 3 cannot equal 0, and therefore x cannot equal 0, nor can x equal -3. So those are where our discontinuities are going to be. And so you're going to piece together from these two discontinuities, you're going to have if you take these on a number line and you mark these discontinuities where x equals -3 and x equals 0, what that's going to look like is you're going to have these open circles there, and you're going to have everything to the left of -3, everything in between -3 and 0, and also everything to the right of 0. And so the correct answer for this is going to be answer choice D. And then you can also graphically verify this. I think I have this pre-entered in the calculator. And yeah, I have it in orange. Let me go ahead and clear this out here. Okay, and then activate this orange one. There it is. That function is activated. Graph. And what you see is a discontinuity where x equals 3. You don't see one, x equals -3. You don't see 1 or x equals 0. Now, if you went ahead and just went by the graph alone, you could possibly enter answer choice B. But you have a removable discontinuity where x equals 0, and removable because this x in the denominator will be canceled out by this x squared in the numerator. And what that looks like in the calculator, how you can really verify that, is take a look at the table view, and you're going to see an error there where x equals -3, and likewise where x equals 0. So that would leave our domain as given answer choice D. Next one we're going to look at is problem 19. 18, you guys did a great job on this rational roots theorem problem. Okay, if f of x equals x plus 4 and g of x equals 3x squared, what is g of f of x? Well, what you're going to do is for g of f of x, g of f of x, what that means is you plug this f into that x right here. So what that's going to be, it's going to be 3, and in the place of this, I'm going to put 3, I'll leave that for x squared. We're going to take that x plus 4 and put it right in here, like this. So x plus 4. And then, so now what you need to do is you need to square out this x plus 4, which you can do a number of different ways. I'm just going to rewrite this as x. You have first squared plus 2 times the first and last plus last squared, which is going to be 16. And then if you go ahead and multiply through, you're going to get 3x squared plus 24x plus 48. So a composition of functions problem here, and answer choice B is our correct answer for that one. Next, we have problem 20. This one here, problem 20, has to do with the fundamental theorem of algebra. And fundamental theorem of algebra. And what that is that the number of zeros, real and non-real, is equal to the degree of a polynomial function. So number of roots, or zeros, real and non-real, is 4, is equal to the degree. And what this is you can see 2 real roots here in these 2 x-intercepts, but by definition of fundamental theorem of algebra, you know by definition you must have 4 roots. And it says some of the roots real and non-real, and some of the zeros may be repeated. And then we get back, and that went to problem 3. The first one we went over, we had that root of -5, which was repeated for a multiplicity of 2. So we know by definition, by the fundamental theorem of algebra, we have 4 roots. And so we can cross off A and B automatically. And then we start counting for extrema, which are maximums and minimums. We see 1 extrema here, another here, and finally another one here. So we have 3 extrema. By the way, the number of extrema can only be at most 1 less than the number than the degree of the function. So having 5 extrema, that would be an impossibility. And so our answer choice is going to be C for this one. Okay, the next one we're going to look at is problem 21. If 2 functions f(x) and g of x are inverse of each other, what is g of x if f of x equals x cubed minus 4? And so we get back to here, in this case, the 4-step process of finding the inverse of function. So we want to find f(-1) of x. And remember, these are things to know about inverses of functions. So if we take, we're going to rewrite this as first step number 1 is taking the function and rewriting that as y equals x cubed minus 4. Step number 2 is switching x and y. So we're going to rewrite this as x equals y cubed minus 4. And the next step is solve for y. So if we take, if we add 4 to solve for y, we're going to get y cubed is equal to x plus 4. And the next step we're going to do is we're going to take the cube root of both sides of this, and what we get is we get y is equal to cube root of x, quantity x plus 4. And then we're going to get, finally change back to f negative 1 of x for inverse function notation is equal to the cube root of quantity x plus 4. And then we see that in, that's answer choice G, because we, by definition, we're told that the g of x and f of x are inverse of each other. So that means that D is our correct answer. And you also have, do you remember that thing we did that was things to know about inverses of functions? We had that list here. One of the things is that two functions that are inverses of each other will reflect about the line y equals x. So we go ahead and take this here, and we can put them in the calculator. X cubed minus 4. So we go here. I'm going to go ahead and clear this out. So we have x cubed minus 4 right here. And we have the cube root of, and let's see, where do we get that? See, it's going to be, I think it's math 4, cube root of I think it's x plus 4, isn't it? Yeah, x plus 4. And we graph these two functions together. We see them look like this, and they reflect about the line y equals x. And let's get that y equals x like this. And it's not like 100% proportional. To get the proportionality right, if we press zoom 5, we should get our proportionality put in place. That you can see that the lavender and green functions reflect about the blue y equals x right there. Okay, so that's number 21. Next thing we get to is problem 23. Problem 23, Hannah was given a rational function, and this fx equals x plus 3 over quantity x squared minus 9 minus 2. And so we're going to graph that. It says, what discontinuities did Hannah discover upon her investigation of this function? Well, and you're given a bunch of answer choices. So let's go ahead and look at them just by graphing. Go to the calculator. I'm going to go ahead and get rid of all these here. Okay, so we come down here to Hannah's situation, and we enter that. This is what we see. And so we see we'd have an infinite discontinuity at x equals 3. So I'm going to go to x equals 3. We got to have a infinite discontinuity. That's a removable discontinuity. Infinite discontinuity at x equals negative 3. Know that infinite discontinuities at x equals 3. We do have an infinite discontinuity at x equals 3. So we're down to between answer choices A and D. And so basically we have to decide which, if we have another discontinuity at x equals negative 3, which we don't see here, that means answer choice A will be right. And if we go ahead and, I'm going to do this without a calculator first. If we come here and we put in, let me see here. Okay, come here and we rewrite this as f of x. And we factor the denominator to quantity x plus 3. I don't know what that's doing try it again. X, there we go, x plus 3. So it's going to x minus 3. On the outside we have plus 2. Well, the x plus 3 over x plus 3 will cancel each other. So that means we have, well, we know x cannot equal -3. And because we were able to remove this algebraically, that's how we get a removable discontinuity at x equals -3. And obviously from the graph, we saw that vertical asymptote here where x equals 3. And so A is going to be our correct answer. Now, one last thing is looking at the table view, we should be able to see at x equals -3, that's where you see that error where we don't see anything on the graph. And then we go to x plus 3, this x plus 3 is the one we actually see by that vertical asymptote in the graph. And the last one we're going to look at here is problem 26. Problem 26 is conveniently put right next to problem 25. In problem 25, you're looking for the height of that soccer ball when kicked. And whereas on problem 26, you're looking for the time it takes to reach that maximum height. And so by having 25 and 26 together, that was actually a clue to help you get that right. I think where I see Brandon had a problem, I think what he had is I think he didn't have it says to the nearest tenth of a second. So that means that the answer we're going to look at is going to be something point something probably, or to the nearest tenth it could be like 2.0 possibly, but that's what your answer is going to look like when you're looking for tenths. So let's go ahead and look at this. I have previously entered this into the calculator below here in Y8. So I'm going to cancel, clear that, go down to Y8 and activate that. And when we graph this, we don't see a whole lot because we need to change the window. I'm going to change the window so we get the maximum. So I'm going to go for the 0 to 5 seconds. And I'm going to go I go from -10 up to, I don't know if it's 100 would get it. But let's go ahead and take a look here. So I'm going to go 0 to 5 for the X. And then for the maximum, I'm going to put 100. And I think I'm going to go by tens here and see if we have everything, if we can see everything here. Yeah, we see a maximum right here. Now Brandon did pick 2 as the answer, and he didn't get it right. And you can see between seconds 2 and 3 is where the maximum height is reached. So you can tell that do this a number of different ways. I'm going to show you 3 different ways to do this in a calculator. One of which is go ahead and go to trace right up, and what you do is you can trace and you can see x equals 2.5, y equals 95.5, and if you've tightened this up pretty well, you're going to be able to see that y still getting higher as we go to the left, still getting higher. So we're kind of topped out about right here. It looks like, okay, we're going lower. Okay, we're going. Yeah, so this is the highest we see here, and it looks like 2.4 is as close as we're going to get. And so 2.4 based on tracing would be right. We can get exactly using the, if I go to second trace and maximum, I go to the left here of the maximum, press enter, and press enter again twice. And we get x equals 2.406. So that's going to be 2.4 comma 95.6. So 2.4 comma 95.6, and 2.4 is what we want. And to the nearest tenth, it is going to be 2.4. So we can put in 2.4. So if you put in just 2, you weren't rounding to the nearest tenth. You're rounding to the nearest second if you put in 2 as opposed to 2.4. So 2.4 is our correct answer. One last way I'm going to show you to do this is how to do this. If you go to table view, one thing you can do is you can go to table set. And since we know we need to be to the nearest tenth, and I'm going to start here at table start at 2, I'm put delta table here as 0.1. And so we put 0.1 here. That means we can go to the table view and we're going to see which decimal value gives us the highest value. If we go to table view from here, we can go right over here and we should be able to see as we proceed down here to that 2.4 is the nearest tenth that gives us the highest amplitude of the output value. So that's another verification. So those are the 10 that I want to go over again. Overall, this was a good result from the test. Some very challenging problems that a lot of you guys did great on. So I just wanted to. It seems like removable discontinuities was the bugaboo that got more people than not. So something to look ahead at for revising my instruction for next year, and also for reminding you going on. As far as removable discontinuity, those of you going into calculus next year, it's going to come into play somewhat when we go into limits, the holes, and point discontinuities. So that's it. Good luck, ladies and gentlemen, and as always, thanks for viewing.